6.3, for the rest of this, we will be talking about direction angles. Prior to this, whenever discussing the direction that a vector was going, we have simply referred to essentially its slope, saying it went up or down and then left or right. Moving forward, we will now refer to it with the direction angle, or the angle in which it went. Very similar to chapter 5 in our unit circle, all of our angles we dealt with then. So to start off with, our direction angle, just like it's always been, is based off of this positive x-axis. So if I had like an angle over here in quadrant 3, my direction angle is that whole thing from 0 past 180, whatever that is. Your direction angle for vector u, and I am going to call this vector u, is between 0 and 360, or between 0 and 2 pi if you are in radians. So if I ever give you, or you find a direction angle that's outside of that range, make sure you convert it using your coterminal angles back to this range. When you describe vector u in component form, you have your horizontal, which is like your x, and your vertical component, which is like your y. Just like back in our unit circle, where x related to your cosine of your angle and y related to your sine of your angle, that will still happen. You also will have, if you're not in component form, if you're using your I and j, your linear combination, it would be cosine of your angle times that I vector, your horizontal vector, and sine times the j. Now the vector I've described here is a unit vector, which again just means it has a length or a magnitude of 1. If I want you to find vector v, which I say goes in the same direction, then you're going to take whatever your magnitude is for vector v and multiply it, if it's in component form, by cosine of theta, sine theta. If it's in that linear combination, you're still going to take that magnitude of v, you're going to multiply it by the cosine of theta times I, and you'd multiply it by that horizontal component, so sine of theta times j. A lot of the times, to abbreviate that, we call this first piece the magnitude of v times cosine of theta a, magnitude of v times cosine of theta, or sorry, times sine of theta would be b. So this is really a times I plus b times j, where I and j are still those unit vectors, I in the vertical, sorry, horizontal direction, j in the vertical direction, and a and b would just be scalars or numeric values, whatever your magnitude times cosine of your angle was. To find that vector, if you think back to your unit circle, tangent was the same as sine over cosine. Notice that sine went over here with b, cosine went over here with a. So even if I have that magnitude in front of it, when I divide, it's in front of both of them, it is going to cancel. So this is essentially b over a. So to find my direction angle, this is like the big kicker here. Your direction angle is tangent inverse, and I'm going to say b over a, but it's just your vertical over your horizontal component, whatever those may be.
Okay.
So for each of these, we're going to find our direction angles. You may leave it written with the I and the j. I personally will say I do not like it written that way. It's always easier for me to change everything to component form, I don't know how much of a difference it's making for these two specific problems, but if you're like adding or subtracting or multiplying them, I do think it makes a difference. So I know that tangent of theta equals my vertical over my horizontal. So in this case, tangent of theta equals 1 somewhere. Tangent equals 1, if you recall, at those 45-degree marks. So I would say 45 degrees. And if you did use your calculator, you would get 45 degrees. You need to be able to do this both with and without a calculator. If they're on the unit circle, I would probably expect you to do it without a calculator. The one thing you want to always check is your quadrant. Positive and positive does put me in quadrant 1. So this is the answer I get, because if you recall, tangent also equals 1 at 225 degrees, but that's down in quadrant 3, so that's not the one we want. Try this one on your own. So I have this set up over here. You're welcome to write it with the theta equals the tangent inverse if that is more pleasing to you, as long as you know you are technically doing tangent inverse. Now my issue here is this does not happen on the unit circle, so I would need to go to my calculator. When I type that into my calculator, and I am currently in degree mode, I get negative 53.13 degrees. That is not between 0 and 360, so I need to get it there. I also need to realize that this, as always, is my reference angle. My calculator will only ever give me my reference angle. If I look at this angle here, or sorry, this vector here, positive for my horizontal and negative for my verticals, that's these. This is somewhere in quadrant 4. So that means that this angle here is 53.13 degrees. I need to know the rest of it. So I'm going to add 360 to that, or I could say 360 minus that 53. But to get this into quadrant 4, that gives me 306.87 degrees. That is my direction angle, because that is the quadrant where this angle is. Find the component form of the vector that represents the velocity of an airplane descending at a speed of 100 miles per hour at an angle of 210 degrees. So at an angle of 210 degrees, I have an airplane. It is flying at a speed of 100 miles per hour. Find the component form of the vector that represents this velocity. So for my vector, if you recall, you do your magnitude of the vector, component form, so that's with the brackets, times cosine of my angle, sine of my angle. So my magnitude is 100, my angle is 210 degrees. Now, 210 is on my unit circle, so this should be done without a calculator. Cosine of 210 would be negative radical 3 over 2. Sine of 210 would be a negative 1/2. When I multiply my 100 to those, I get negative 50 radical 3, negative 50. If I asked for it as a linear combination, that would be negative 50 radical 3i minus 50j. Do be careful or pay attention whenever you have problems where they're written like this. Sometimes I might write it like this and then ask you, hey, what's my direction angle? It would just be the angle that's written right there, because it's the same as this angle. Or what's my magnitude? Though that's whatever's up front. Find the component form of the sum of u and v. So first off, component form. That means I need to get these guys into component form. So for u, I'm going to take my magnitude of u, multiply it by cosine of the direction angle of u, and sine of the direction angle of u. I'm going to do the same thing for v. And I will be adding these once I get those. So my magnitude of u is 35. Cosine of 25 degrees, because that's my direction angle, sine of 25 degrees. Go ahead and fill that in for v. Once you've done that, go ahead and do your cosine and your sine. Now, for this 25 degrees, that's not on my unit circle, so I'm just going to be typing that into my calculator. Work on v. I'll add it up here in a minute. Once I've actually done the cosine and the sine, I can distribute that 35. So for vector u, that component form is actually 14.81. For vector v, you should have gotten negative 25 and 25 radical 3. If you want to see how I got that, my magnitude of v was 50. My direction angle was 120 degrees, so I could fill that in for each of these. Then, thinking about my unit circle, when I do cosine of 120 degrees, I get a negative 1/2. And for sine, you should get radical 3 over 2. So that is how I ended up with the negative 25 and the 25 radical 3. Now I would say when you add these, I would want to keep it an exact answer, except for that this side has exactals on the unit circle and this side doesn't. Since they're not both an exact answer, you can just go ahead and type them in and get your decimal for each of these. My horizontal component would be 6.71. My vertical would be 58.11. That is my sum of u and v. Alright, now I'm going to show you how to find the angle between these two vectors. For right now, you'll be doing that using your law of cosines, because it is important that we remember and reuse information we've learned in previous sections. In 6.4, you will get an actual easier formula for this. The best way to do this for right now is to first off, rewrite each of these in component form, but then to draw these vectors. So when you get to this section on your homework, maybe make a note, because the directions literally read, find the angle between the given vectors. It might even say, with the law of cosines. You need to draw your vectors. So take a second and draw all of these. Here's vector v, vector w. Now that does not create a triangle. To create a triangle, I need to connect that third side. We're going to call that vector u. Vector u, you could either think of as the subtraction with v minus w or w minus v, but in either case, it is this vector. I'm going to look at it going from left to right, so that's 2, negative 2. Those are my three vectors. This is the angle between v and w, so this is the angle I'm trying to find. I would say let's take a second and go ahead and find your magnitudes for all three of those, because you will need those. Remember, magnitudes in this case, I mean it's a triangle, are essentially just the length of each side. So you're doing law of cosines to find this angle, you have the length of all your sides. Go ahead and set up your law of cosines to find an angle. It's the length of the two sides next to it, so that'd be the magnitude of v and the magnitude of w, those are squared and added, minus the magnitude or the length of the side across from it, which would be u squared, all over 2 times the magnitude of v times the magnitude of w. Go ahead and plug those in and see what you get. So I did go ahead and simplify my denominator down here. This is now 4 radical 5, which would become 1 over radical 5, which is radical 5 over 5. I go through all that work, and unfortunately that's not on my unit circle anywhere, so I am going to be doing cosine inverse to get my angle. When I do that, theta equals 63.5 0.43 degrees.